sklearn config context. Description: the config context in scikit-learn sklearn is a powerful tool for managing and customizing the configuration of your machine learning pipeline. It provides a structured way to set and modify various aspects of your model building process, ensuring consistency and reproducibility. Inputs. Data: the input data, usually in the form of a pandas data frame or NumPy array, containing features and target variables. Model parameters: the hyperparameters of the chosen machine learning model, such as the number of estimators in a random forest or the regularization strength in a linear regression. Preprocessing options: the methods to be used for data preprocessing, such as feature scaling, imputation of missing values, and encoding categorical variables. Evaluation metrics: the criteria used to evaluate the performance of the model, such as accuracy, precision, recall, or F1 score. Outputs. Trained model: the fitted machine learning model, ready for making predictions on new data. Performance metrics: the evaluated scores of the model based on the chosen metrics. Model insights: information about the model's learned patterns and relationships, potentially including feature importance or coefficient values. Steps. Data preparation: this involves cleaning, transforming, and engineering features in the data. Model selection: choosing the appropriate machine learning model based on the problem and data. Characteristics. Model training: fitting the model to the prepared data, learning patterns and relationships from the input features. Model evaluation: assessing the model's performance using various metrics on a separate evaluation dataset or using cross-validation. Model tuning: optional, optimizing the model's hyperparameters to improve its performance using techniques like grid search CV or randomized search CV. Metrics. Accuracy: the percentage of correctly classified instances. Precision: the ratio of correctly predicted positive instances to the total number of instances predicted as positive. Recall: the ratio of correctly predicted positive instances to the total number of actual positive instances. F1 score: a harmonic mean of precision and recall, providing a balanced measure of performance. Mean squared error MSE: the average of squared differences between actual and predicted values, commonly used for regression problems. Root mean squared error RMSE: the square root of MSE, providing a more interpretable measure of error. Visualization plots. Confusion matrix: a visual representation of the model's classification performance, showing true positives, true negatives, false positives, and false negatives. ROC curve: a graphical representation of the trade-off between true positive rate sensitivity and false positive rate 1 specificity for different classification thresholds. Precision recall curve: a plot showing the relationship between precision and recall for different thresholds. Feature importance plot: a visualization that shows the relative importance of features in the model's decision-making process. Residual plot: a plot of the difference between predicted and actual values, used to assess model assumptions and identify potential issues. Fine-tune parameters. Regularization strength: for linear models, controlling the complexity of the model and preventing overfitting. Number of estimators: for ensemble models like random forest, determining the number of trees or base models used in the ensemble. Maximum depth: for decision tree-based models, limiting the depth of individual trees to control complexity. Learning rate: for gradient-based models, determining the step size used in the optimization process. Uncertainty methods. Confidence intervals: estimating the range of plausible values for the model's predictions based on the uncertainty in the training data. Bayesian methods incorporating prior knowledge and uncertainty into the model's estimation process. Ensemble methods using multiple models to make predictions and aggregating their results. Reducing the impact of individual model errors. Challenges and fixes. Challenge 1: overfitting when the model performs well on the training data but poorly on unseen data. Sample use case that resulted in challenge 1: a complex model with many features and a small training dataset may lead to overfitting. Fixes to challenge 1. Use regularization techniques like L1 or L2 to penalize complex models. Simplify the model by reducing the number of features or using a simpler model structure. Increase the size of the training dataset. Challenge 2: underfitting when the model is too simple to capture the underlying patterns in the data. Sample use case that resulted in challenge 2: a linear model may underfit a dataset with nonlinear relationships between features and the target variable. Fixes to challenge 2: use a more complex model structure, such as a nonlinear model like a decision tree or neural network. Add more features to the dataset that capture the complex relationships. Consider feature engineering to create more informative features. Challenge 3: data imbalance when the target variable has a skewed distribution, leading to biased predictions. Sample use case that resulted in challenge 3: in a fraud detection dataset. The number of fraudulent transactions is significantly lower than legitimate transactions. Fixes to challenge 3: use resampling techniques like oversampling or undersampling to balance the classes. Employ cost-sensitive learning, where misclassification costs are adjusted based on the class distribution. Use appropriate evaluation metrics that account for data imbalance, such as precision recall curve or F1 score. Challenge 4: missing values. The presence of missing data can affect the model's performance. Sample use case that resulted in challenge 4: missing values in certain features of a medical dataset might make it difficult to train a reliable model. Fixes to challenge 4: use imputation techniques to fill in missing values based on other features or the distribution of the variable. Remove features with too many missing values. Consider using models that are robust to missing data, such as tree-based models. Challenge 5: categorical features. Handling categorical variables non-numerical is crucial for model training. Sample use case that resulted in challenge 5: a dataset with features like gender, location, or product type needs to be encoded before training. Fixes to challenge 5: use one-hot encoding to create binary features for each unique category. Use ordinal encoding if the categories have a natural order. Consider using models that can handle categorical variables directly, such as decision trees or ensemble models. Challenge 6: high dimensionality when the number of features is very large. It can lead to overfitting and computational inefficiency. Sample use case that resulted in challenge 6: a dataset with thousands of features may require dimensionality reduction techniques. Fixes to challenge 6: use feature selection methods to choose the most relevant features. Use dimensionality reduction techniques like principal component analysis (PCA) or TSNE to reduce the number of features. Challenge 7: scalability. Training models with large datasets can be computationally intensive. Sample use case that resulted in challenge 7: a very large image dataset requires efficient algorithms and resources for training. Fixes to challenge 7: use efficient algorithms and data structures. Employ distributed computing techniques like Spark or Hadoop to distribute the computation across multiple machines. Consider using online learning algorithms that can learn incrementally from data. sklearn base. Description. Explain in detail. The sklearn base module provides fundamental classes and methods for building machine learning models in scikit-learn. It serves as the foundation for creating and managing estimators, transformers, and other essential components within the scikit-learn ecosystem. Inputs. Input 1. Explain in detail. The sklearn base module itself doesn't directly take input data. It primarily defines the structure for building components that will eventually work with data. Input 2. Explain in detail. Outputs. Output 1. Explain in detail. Output 2. Explain in detail. Steps. Step 1. Explain in detail. The sklearn base module defines core classes like base estimator, transformer mixin, and classifier mixin. These classes provide a blueprint for building machine learning components by defining common methods and attributes that ensure consistency and compatibility across different models. Step 2. Explain in detail. By inheriting from these base classes, developers can create custom estimators, transformers, or classifiers while adhering to scikit-learn's conventions. This facilitates model integration, reusability, and interoperability within the scikit-learn ecosystem. Metrics. Metric 1. Explain in detail. Metric 2. Explain in detail. Visualization plots. Visualization plot 1. Explain in detail. Visualization plot 2. Explain in detail. Fine-tune parameters. Parameter 1. Explain in detail. Parameter 2. Explain in detail. Uncertainty methods. Uncertainty method 1. Explain in detail. Uncertainty method 2. Explain in detail. Challenges and fixes. Challenge 1. Explain in detail. Sample use case that resulted in challenge 1. Fixes to challenge 1. Challenge 2. Explain in detail. Sample use case that resulted in challenge 2. Fixes to challenge 2. sklearn getConfig. Description. The getConfig function is a utility function within the scikit-learn sklearn library that provides information about the current configuration of the library. It allows you to retrieve details about various settings, such as the version of scikit-learn, the default settings for data structures, and the installation paths of essential components. Inputs. None. This function doesn't take any specific input arguments. Outputs. A dictionary. The function returns a dictionary containing configuration details about scikit-learn. Steps. Retrieve configuration. The function accesses the internal configuration settings of scikit-learn. Format data. The collected information is organized and formatted into a dictionary structure. Metrics. None. This function doesn't return any metrics. Visualization plots. None. This function doesn't generate any visualization plots. Fine-tune parameters. None. This function doesn't offer any fine-tuning parameters. Uncertainty methods. None. This function doesn't have any uncertainty methods associated with it. Challenges and fixes. Challenge 1. Configuration changes. If you've made custom changes to the scikit-learn configuration, this function will reflect those changes, potentially leading to unexpected behavior if you are not aware of them. Sample use case that resulted in challenge 1. Manually modifying the scikit-learn configuration file, typically found in the site packages directory. Fixes to challenge 1. Review any modifications you've made to the configuration file and ensure they're intended. Reset the configuration to default values if necessary. Challenge 2. Environment differences. The configuration returned by this function can vary depending on the environment, e.g., operating system, Python version. Sample use case that resulted in challenge 2. Running code on a different machine or in a different virtual environment with different scikit-learn installations. Fixes to challenge 2 ensure that the scikit-learn version and dependencies are consistent across different environments to avoid configuration discrepancies. sklearn base estimator. Description: the base estimator class in scikit-learn sklearn is the fundamental building block for creating custom machine learning estimators. It defines the basic structure and methods that all estimators in scikit-learn should adhere to. Inputs: data. The input data for training or predicting, typically represented as a NumPy array or a pandas data frame. Target: for supervised learning, the corresponding labels or target values associated with the data. For supervised learning tasks. Outputs: trained model. After training, the estimator learns a model based on the input data and target values, which can then be used for predictions. Predictions when applied to new data. The trained model generates predictions. Steps: initialization. The init method is called to initialize the estimator with any required parameters. Fit. The fit method is used to train the estimator on the input data and target values. Predict. The predict method is used to generate predictions for new data. Metrics: accuracy, a measure of the proportion of correctly classified instances in a classification task. Precision, the ability of the model to correctly identify positive instances. Recall, the ability of the model to correctly identify all positive instances. F1 score, a harmonic mean of precision and recall. Mean squared error, MSE, a measure of the average squared difference between the predicted and actual values in regression tasks. R squared, a statistical measure that indicates the proportion of the variance in the dependent variable that is explained by the independent variables. Visualization plots. Confusion matrix, a visual representation of the performance of a classification model, showing the number of correctly and incorrectly classified instances. ROC curve, a plot of the true positive rate against the false positive rate for different threshold values. Precision recall curve, a plot showing the relationship between precision and recall for different threshold values. Learning curve, a plot that shows the performance of the model as a function of the size of A. Training data. Fine-tune parameters. Regularization parameters, e.g., L1, L2, used to prevent overfitting by penalizing complex models. Learning rate, a parameter in gradient-based optimization methods that controls the step size for each update. Number of trees for ensemble methods, the number of decision trees used in an ensemble method like random forest. Maximum depth of trees, the maximum depth of individual trees in ensemble methods. Uncertainty methods. Confidence intervals provide a range of values within which the true value is likely to lie. Bayesian inference incorporates prior knowledge and uses probability distributions to estimate the uncertainty in model parameters. Bootstrapping, resampling with replacement to estimate the uncertainty in predictions. Challenges and fixes. Challenge 1: overfitting. The model learns the training data too well and fails to generalize to new data. Sample use case that resulted in challenge 1: using a complex model with too many parameters on a small dataset. Fixes to challenge 1. Use regularization techniques, e.g., L1, L2, to penalize complex models. Use cross-validation to evaluate the model's performance on unseen data. Simplify the model or use a smaller dataset. Challenge 2: underfitting. The model is too simple and fails to capture the underlying patterns in the data. Sample use case that resulted in challenge 2: using a linear model on a nonlinear dataset. Fixes to challenge 2. Use a more complex model that can capture nonlinear relationships. Add more features to the dataset. Increase the complexity of the model by adding more layers or neurons. Challenge 3. Data leakage. Information from the target variable is unintentionally included in training data, leading to artificially high performance. Sample use case that resulted in challenge 3 using a feature that is derived from the target variable during training. Fixes to challenge 3. Carefully select features that are not correlated with the target variable. Use techniques like train test splitting or cross-validation to ensure that the training and testing data are independent. Use domain knowledge to identify and remove features that are likely to leak information. Challenge 4. Imbalanced data. The target variable is not evenly distributed across the classes, leading to biased models. Sample use case that resulted in challenge 4. A dataset where one class is significantly more frequent than the others. Fixes to challenge 4. Use techniques like oversampling, undersampling, or synthetic data generation to balance the dataset. Use class weights to penalize misclassifications of minority classes. Use appropriate metrics that are robust to imbalanced datasets, such as F1 score or AUC. sklearn set config. Description. The setConfig function in scikit-learn sklearn provides a way to modify global settings that affect how sklearn operates. It allows you to control aspects like the default display format for data, the verbosity of warnings, and the parallelism strategy. Inputs. Config. This is a dictionary-like object containing key-value pairs that represent the desired configuration settings. Each key corresponds to a specific configuration option, and its value determines the desired behavior. Outputs. None. The setConfig function doesn't directly return any values. Instead, it modifies the global settings of sklearn, making the changes persistent for subsequent operations. Steps. Setting options. The function takes the provided configuration dictionary and updates the internal settings of sklearn based on the specified keys and values. Applying changes. Once the settings are modified, the changes take effect immediately. Future calls to sklearn functions will use the updated configuration. Metrics. There are no specific metrics associated with setConfig as it doesn't perform any data analysis or model training. Visualization plots. No visualization plots are directly generated by setConfig. Fine-tune parameters. There are no fine-tuning parameters for setConfig itself. Uncertainty methods. There are no uncertainty methods related to setConfig. Challenges and fixes. Challenge 1. Setting incompatible options. If you try to set a configuration option to an invalid value, e.g., a string where an integer is expected, it may lead to unexpected behavior or errors. Sample use case that resulted in challenge 1. Attempting to set print function to an invalid string value. Python. From sklearn, utils import config. Config. setConfig print function invalid string incorrect configuration. Fixes to challenge 1. Ensure you use valid values for each configuration option as documented in sklearn documentation. Refer to the documentation for accepted data types and values for each configuration key. Challenge 2. Overriding default settings unintentionally. Using setConfig can inadvertently override existing default settings, leading to unexpected changes in how sklearn functions operate. Sample use case that resulted in challenge 2. Accidentally changing the default display setting without realizing. Python. From sklearn, utils import config. Config. setConfig display off. This turns off all default displays. Fixes to challenge 2. Carefully review the configuration options you are setting and their potential impact on sklearn's behavior. Be aware of the default settings and ensure your modifications are intentional. Consider using a dedicated configuration file to manage settings consistently. Challenge 3. Inconsistency across multiple scripts or environments. If you use different configurations for different scripts or environments, it might lead to inconsistency in how your code behaves. Sample use case that resulted in challenge 3: setting the verbosity level to warning in one script and debug in another. Python. Script 1. From sklearn, utils import config. Config, set config verbosity warning. Script 2. From sklearn, utils import config. Config, set config verbosity debug. Fixes to challenge 3: maintain a centralized configuration file or use environment variables to manage settings consistently across your projects. This ensures that the same configuration applies across all relevant scripts and environments. sklearn, base, bicluster mixin. Description. Bicluster mixin is a base class for biclustering algorithms in scikit-learn. It provides a common interface for biclustering models and defines several essential methods for bicluster analysis. Inputs: X, a 2D array of shape n samples. N features representing the data to be biclustered. Each row corresponds to a sample, and each column corresponds to a feature. Row labels: a 1D array of shape n samples, indicating the labels or groups of each sample. It is optional and can be used to guide the biclustering process. Aiming to find biclusters that are coherent with the given labels. Column labels: a 1D array of shape n features, indicating the labels or groups of each feature. It is optional and can be used to guide the biclustering process. Aiming to find biclusters that are coherent with the given labels. Outputs: row labels: a 1D array of shape n samples, containing the bicluster assignment for each sample. Column labels: a 1D array of shape n features, containing the bicluster assignment for each feature. Steps: fit. The fit method takes the input data and optional labels and performs the biclustering. Algorithm: assigning samples and features to biclusters based on the chosen biclustering criterion. Predict. The predict method takes a new data point, a single sample or a set of samples, and predicts the bicluster assignment for the input samples. Get indices. The get indices method returns the indices of the samples and features belonging to a specific bicluster. Metrics: silhouette score. The silhouette score measures the similarity between samples within a bicluster compared to other biclusters. It is used to evaluate the quality of the biclustering solution. Kalinski-Haraba's index. The Kalinski-Haraba's index measures the ratio of between cluster variance to within cluster variance. It is another metric to evaluate the quality of the biclustering solution. Visualization plots. Heatmap. A heat map visualization of the data matrix with biclusters highlighted. It helps identify patterns and relationships among samples and features within each bicluster. Dendrogram. A dendrogram plot showing the hierarchical structure of the biclustering results. It helps visualize the relationships between different biclusters and understand the hierarchical clustering process. Fine-tune parameters. N clusters. The number of biclusters to find. Niter. The number of iterations to run the biclustering algorithm. Random state. The random seed used for initialization and random sampling. Uncertainty methods. Bootstrapping. By resampling the data with replacement and performing biclustering on each resampled dataset. We can estimate the variability of the biclustering results and assess the uncertainty associated with each bicluster. Challenges and fixes. Challenge 1: choosing the appropriate number of biclusters n clusters. Sample use case: if the number of biclusters is too small, it may fail to capture all the underlying patterns in the data. If the number of biclusters is too large, it may lead to overfitting and produce meaningless biclusters. Fixes: use elbow method or silhouette score to determine the optimal number of biclusters. Challenge 2: handling high-dimensional data. Sample use case: biclustering algorithms can be computationally expensive and challenging for high-dimensional datasets. Fixes: apply dimensionality reduction techniques such as PCA or feature selection before biclustering. YAML. sklearn show versions. Description displays the versions of scikit-learn and its dependencies. Inputs: none. Outputs: version information for scikit-learn and its dependencies. Python version, NumPy version, SciPy version, joblib version, threading version. Steps: retrieves version information from the installed packages. Formats the information in a user-friendly way. Metrics: none. Visualization plots: none. Fine-tune parameters: none. Uncertainty methods: none. Challenges and fixes: none. sklearn, base, classifier mixin. Description: classifier mixin is a base class in scikit-learn sklearn that provides a common interface for classification algorithms. It defines the basic methods that all classifiers in sklearn should implement. This ensures consistency and allows for seamless integration with other sklearn components. Inputs: X. The input data. Typically a 2D array where each row represents a data point and each column represents a feature. Y. The target labels. A 1D array containing the true class labels for each data point. Outputs: predictions. A 1D array containing the predicted class labels for the input data. Probabilities. Optional. A 2D array where each row represents a data point and each column represents the probability of belonging to a specific class. Steps: training. The classifier is trained on the input data X and target labels Y. This step involves learning the underlying patterns and relationships between features and classes. Prediction. The trained classifier is used to predict the class labels for new unseen data. Metrics: accuracy. The proportion of correctly classified instances. Precision. The proportion of correctly predicted positive instances among all instances predicted as positive. Recall. The proportion of correctly predicted positive instances among all actual positive instances. F1 score. The harmonic mean of precision and recall. Visualization plots. Confusion matrix. A visual representation of the classification results, showing the number of true positives, true negatives, false positives, and false negatives. ROC curve. A plot showing the trade-off between true positive rate sensitivity and false positive rate 1 specificity for different classification thresholds. Precision recall curve. A plot showing the trade-off between precision and recall for different classification thresholds. Fine-tune parameters. Regularization strength controls the amount of penalty applied to model complexity, helping to prevent overfitting. Number of estimators for ensemble methods like random forests. This parameter determines the number of individual models combined. Learning rate for gradient-based algorithms. This parameter controls the step size during optimization. Uncertainty methods. Confidence scores. Some classifiers provide confidence scores for each prediction, indicating the classifier's level of certainty about the predicted class. Bayesian methods approaches like Bayesian classification can provide a probabilistic interpretation of the predictions, incorporating uncertainty, challenges and fixes. Challenge 1: overfitting the model may perform well on the training data but poorly on unseen data. Sample use case: a model trained on a small dataset with many features may overfit to the specific examples in the training set. Fixes: regularization: add penalties to the model complexity to discourage overfitting. Cross-validation: split the data into training and validation sets to assess model performance on unseen data. Challenge 2: class imbalance: when one class has significantly more instances than others, the model may bias towards the majority class. Sample use case: in fraud detection, the number of fraudulent transactions is usually much smaller than legitimate transactions. Fixes: oversampling duplicate instances of the minority class to balance the dataset. Undersampling: remove instances from the majority class to balance the dataset. Cost-sensitive learning: assign different costs to misclassifications depending on the class, making the model more sensitive to the minority class. Challenge 3: data dimensionality: high-dimensional datasets can lead to computational challenges and potentially overfitting. Sample use case: text data often has a very high number of features words. Fixes: feature selection: select a subset of the most relevant features. Dimensionality reduction: apply techniques like PCA to reduce the number of dimensions while preserving important information. Challenge 4: missing values: incomplete data can affect model performance. Sample use case: data may have missing values due to data collection errors or other reasons. Fixes: imputation: fill missing values with estimated values based on available data. Model-based imputation: use a model to predict the missing values. sklearn, Bayes, cluster mixin. Description: the cluster mixin is a base class for clustering estimators in scikit-learn. It defines methods for fitting and predicting cluster labels, as well as methods for accessing the cluster centers or other cluster-related information. Inputs: X. This is the input data that you want to cluster. It can be a 2D array or a sparse matrix. Outputs: labels. The cluster labels for each data point in the input dataset X. Steps: fit. This method fits the clustering model to the input data X. It learns the underlying cluster structure from the data. Predict. This method predicts the cluster labels for new data points that were not used during the fitting process. Metrics: silhouette score. This metric measures how similar an object is to its own cluster compared to other clusters. A higher score indicates a better clustering. Kalinske-Haraba's index. This metric measures the ratio of between cluster variance to within cluster variance. A higher score indicates a better clustering. Davies-Bouldin index. This metric measures the ratio of within cluster distances to between cluster distances. A lower score indicates a better clustering. Visualization plots: scatter plot. This plot helps visualize the clusters in 2D or 3D space, allowing you to visually assess the quality of the clustering. Dendrogram: a dendrogram is a tree-like diagram that shows the hierarchical relationships between clusters. Fine-tune parameters: n clusters. This parameter specifies the number of clusters to be formed. Random state: this parameter controls the randomness in the clustering algorithm. Setting it to a fixed value ensures reproducible results. Challenges and fixes: Challenge 1: choosing the right number of clusters. K. Determining the optimal number of clusters is a crucial step in clustering. Sample use case: you might have data where you are unsure of the ideal number of clusters for your application. Fixes: Elbow method. Plot the inertia sum of squared distances to the cluster center for different values of k. Look for an elbow point where the inertia decreases sharply. Silhouette analysis. Calculate the silhouette score for different values of k. The optimal k is the one that produces the highest silhouette score. Challenge 2. Dealing with outliers. Outliers can significantly affect the clustering results. Sample use case. You have data with some unusual data points that might be distant from any cluster center. Fixes. Preprocessing. Remove or handle outliers before fitting the clustering model. This could involve using outlier detection techniques or feature scaling methods. Robust clustering algorithms. Explore robust clustering algorithms that are less sensitive to outliers, such as k-medoids. Challenge 3. Handling high-dimensional data. Clustering high-dimensional data can be challenging. Sample use case. Your data has a large number of features. Fixes. Dimensionality reduction. Apply techniques like PCA or T-SNE to reduce the dimensionality of data before clustering. Feature selection. Select the most relevant features for clustering, potentially improving the results. Subspace clustering. Consider methods that search for clusters in different subspaces of the data. sklearn. Base. Density mixin. Description. The density mixin is a mixin class in scikit-learn that provides a common interface for estimators that can estimate the probability density function (PDF) of data. This interface defines a method scoreSamples that calculates the log likelihood of each sample. Under the estimated PDF, estimators that inherit from this mixin can be used for density estimation tasks such as anomaly detection, outlier detection, and probabilistic classification. Inputs. Data. The input data for which the probability density function is to be estimated. This can be a NumPy array or a Pandas data frame. Outputs. Log likelihoods. The scoreSamples method returns the log likelihoods of each data sample under estimated PDF. Steps. Fit. The estimator is first fitted to the training data, which involves learning the parameters of the PDF from the data. scoreSamples. Once fitted, the scoreSamples method can be used to calculate the log likelihoods of new data samples. Metrics. Log likelihood. The log likelihood is a commonly used metric to evaluate the goodness of fit of a density estimation model. Higher log likelihoods indicate a better fit. Visualization plots. Density plot. The estimated PDF can be visualized using a density plot, which shows the probability density across the range of values in the data. Fine-tune parameters. Bandwidth. This parameter controls the smoothness of the estimated density function. A larger bandwidth results in a smoother estimate, while a smaller bandwidth leads to a more detailed estimate. Uncertainty methods. Confidence intervals. Confidence intervals can be estimated for the estimated density function to quantify the uncertainty in the predictions. Challenges and fixes. Challenge 1. Overfitting. If the bandwidth is too small, the model might overfit to the training data and fail to generalize well to new data. Sample use case that resulted in challenge 1 using a small bandwidth on a dataset with high noise or outliers can lead to overfitting. Fixes to challenge 1. Increase the bandwidth or use a regularization technique to prevent overfitting. Challenge 2. Underfitting. If the bandwidth is too large, the model might underfit the data and fail to capture the true underlying density function. Sample use case that resulted in challenge 2 using a large bandwidth on a dataset with complex structure can lead to underfitting. Fixes to challenge 2. Decrease the bandwidth or use a more sophisticated density estimation model. sklearn, base, regressor mixin. Description. Regressor mixin is a base class in scikit-learn sklearn that defines the common interface for regression models. It provides a set of methods and attributes that all regression models in sklearn should implement. This class acts as a blueprint for building regression models, ensuring consistency and interoperability within the sklearn ecosystem. Inputs. Training data. This includes the features-independent variables used to predict the target variable. The features can be represented as a NumPy array or a pandas data frame. Target variable. This is the variable that the model aims to predict. It should be a NumPy array or a pandas series. Outputs. Trained model. After fitting the model with training data, the regressor mixin object itself represents the trained model, ready to make predictions. Predictions when given new input data features. The trained model can generate predictions for the target variable. These predictions are typically in the form of a NumPy array. Steps. Initialization. The regressor mixin class is typically inherited by specific regression models, like linear regression, decision tree regressor, etc. When initializing these models, you might configure certain parameters like regularization strength, tree depth, etc. Fitting. The .fit method is called on the model with training data features and target variable. This step trains the model by learning the relationships between features and the target. Prediction. Once trained, the predict method can be used to generate predictions on new input data. The model takes the features as input and outputs predicted values for the target variable. Metrics. Mean squared error. MSE calculates the average squared difference between actual values and predicted values. Root. Mean squared error. RMSE. The square root of MSE, providing a measure of error in the same units as the target variable. Mean absolute error. May computes the average absolute difference between actual and predicted values. R squared represents the proportion of variance in the target variable explained by the model. Visualization plots. Scatter plot of actual vs predicted values helps visualize the model's performance and identify potential biases or outliers. Residual plot displays the difference between actual and predicted values, revealing patterns in the model's errors. Fine-tune parameters. Regularization strength, e.g., L1. L2 controls the complexity of the model and helps prevent overfitting. Tree depth. For tree-based models limits the depth of the decision tree, reducing complexity and preventing overfitting. Learning rate. For gradient-based models controls the step size during optimization, influencing the speed and stability of training. Uncertainty methods. Confidence intervals provide a range around the prediction, indicating the model's uncertainty. Prediction intervals extend confidence intervals to account for both model uncertainty and randomness in the data. Challenges and fixes. Challenge 1. Overfitting. The model performs well on the training data but generalizes poorly to unseen data. Sample use case that resulted in challenge 1. A model trained on a small data set might learn specific patterns in the training data that are not representative of the wider population. Fixes to challenge 1. Regularization techniques. L1. L2 penalize complex models, reducing overfitting. Cross-validation. Split the training data into folds. Train on different folds, and evaluate on the remaining fold to assess generalization performance. Challenge 2. Underfitting. The model is too simple and cannot capture the underlying patterns in the data. Sample use case that resulted in challenge 2. A linear model might fail to capture nonlinear relationships in the data. Fixes to challenge 2. Increase model complexity. Explore more complex models like polynomial regression or decision trees. Feature engineering. Create new features that might capture the nonlinear relationships in PE data. Hyperparameter tuning. Optimize parameters like tree depth or regularization strength to find the best fit for the data. Challenge 3. Data leakage. Information from the target variable is unintentionally included in PE features, leading to overly optimistic performance. Sample use case that resulted in challenge 3. Using a feature that is derived from the target variable for training. Fixes to challenge 3. Careful feature selection. Ensure that features used for training do not directly depend on or contain information about the target variable. Data preprocessing. Remove any potential leakage sources from the data before training. Challenge 4. Multicollinearity. High correlation between features can make it difficult for the model to determine the individual effects of each feature. Sample use case that resulted in challenge 4. 2 features that measure similar aspects of the data may be highly correlated. Fixes to challenge 4. Feature selection. Choose a subset of features that are not highly correlated. Regularization techniques penalize models that rely heavily on highly correlated features. sklearn, base, transformer mixin. Description. The transformer mixin class in scikit-learn is a base class for all transformers. It provides a standard interface for transforming data, ensuring consistency across different transformers. Transformers are often used as part of a scikit-learn pipeline, where they are applied to the data before it is passed to a model. Inputs. Data. The input data to be transformed. It can be a pandas data frame, a NumPy array, or any other format that the specific transformer supports. Outputs. Transformed data. The output of the transformer is the transformed data, which is typically a modified version of the input data. The specific format of the output depends on the transformer. Steps. Fit. The fit method learns the parameters of the transformer from the input data. This step is typically used to calculate statistics, create mappings, or learn other information from the data. Transform. The transform method applies the learned parameters to the input data and produces the transformed output. Metrics. Accuracy measures the percentage of correct predictions. Precision measures the percentage of correctly predicted positive instances out of all instances predicted as positive. Recall measures the percentage of correctly predicted positive instances out of all actual positive instances. F1 score. A harmonic mean of precision and recall. Visualization plots. Scatter plot visualizes the relationship between two variables. Histogram shows the distribution of a single variable. Boxplot displays the distribution of data using quartiles and outliers. Fine-tune parameters. Parameters specific to each transformer. Transformers have various parameters that can be tuned to optimize their performance. Refer to the documentation of specific transformers for details. Uncertainty methods. Confidence intervals provide a range of values within which the true value of a parameter is likely to fall. Bootstrap resamples the data multiple times to estimate the variability of a statistic. Challenges and fixes. Challenge 1. Data leakage. The transformer may learn information from the target variable, which can lead to overfitting. Sample use case that resulted in challenge 1. Using a transformer that calculates the mean of a feature within a target class. This could lead to the transformer knowing the target class for unseen data. Fixes to challenge 1. Use data splitting techniques, such as train test split, to avoid data leakage during fitting. Challenge 2: memory issues. Large datasets can consume significant memory, particularly during the fitting process. Sample use case that resulted in challenge 2: applying a transformer to a very large dataset, such as a billion rows. Fixes to challenge 2: use data partitioning techniques or transformers that are memory efficient. Challenge 3: overfitting. The transformer may overfit the training data, resulting in poor performance on unseen data. Sample use case that resulted in challenge 3: using a transformer that learns highly complex patterns from the training data. Fixes to challenge 3: use regularization techniques, such as L1 or L2 regularization, to prevent overfitting. Challenge 4: handling missing values. The transformer may not handle missing values appropriately, leading to errors or biased results. Sample use case that resulted in challenge 4: applying a transformer to data with missing values, without specifying how to handle them. Fixes to challenge 4: impute missing values using appropriate methods, such as mean or median imputation. Challenge 5: feature scaling. The transformer may not perform well if the input features are on different scales. Sample use case that resulted in challenge 5: applying a transformer to data with features on different scales, such as age in years and income in dollars. Fixes to challenge 5: use feature scaling techniques, such as standardization or normalization, to bring features to the same scale. sklearn, base, Method Estimator Mixin. Description: the Method Estimator Mixin is a base class that allows you to create your own custom method estimators, which are estimators that wrap other estimators to enhance their capabilities. It provides the getParams and setParams methods, which are essential for implementing the fit, predict, and score methods of your custom estimator. Inputs: base estimator. This is the estimator that your method estimator wraps. It can be any scikit-learn estimator, such as a classifier, regressor, or clustering algorithm. Additional parameters: your method estimator might need additional parameters to customize its behavior. These parameters can be passed to the init method. Outputs: fitted method estimator. The fitted method estimator, which can be used for prediction or other tasks. Predictions: the predictions made by the method estimator on new data. Scores: the performance scores achieved by the method estimator. Steps: initialization: the method estimator is initialized with the base estimator and any additional parameters. Fitting: the base estimator is fitted on the training data, and the method estimator may perform additional operations during this phase. Prediction: the fitted method estimator predicts the target variable for new data. Scoring: the performance of the method estimator is evaluated using various metrics. Metrics: the metrics used to evaluate the performance of the method estimator depend on the specific task and the base estimator being wrapped. Visualization plots: the visualization plots will depend on the specific task and the base estimator. Fine-tune parameters: the fine-tuning parameters will vary depending on the specific method estimator implementation. Uncertainty methods: the uncertainty methods used will depend on the specific method estimator implementation. Challenges and fixes: challenge 1: the method estimator might not be able to properly handle the output of the base estimator. Sample use case that resulted in challenge 1: a method estimator wrapping a clustering algorithm might need to process the cluster labels in a specific way. Fixes to challenge 1: modify the fit, predict, or score methods of the method estimator to handle the output of the base estimator correctly. Challenge 2. The method estimator might not be able to properly handle the parameters of the base estimator. Sample use case that resulted in challenge 2. A method estimator might need to adjust the parameters of the base estimator based on the specific task. Fixes to challenge 2. Implement custom getParams and setParams methods to manage the parameters of the base estimator. sklearn, base, one-to-one feature mixin. Description: the one-to-one feature mixin class in scikit-learn is a base class for transformers that implement a one-to-one mapping between input features and output features. This means that for each input feature, there will be a corresponding output feature. This is in contrast to other transformers that might combine multiple input features to create a single output feature or create multiple output features from a single input feature. Inputs. Input: a NumPy array or pandas data frame containing the input features. The input data should be in a suitable format for the specific transformer that is inheriting from one-to-one feature mixin. For example, if using a transformer for scaling the input features, the input data should be numerical. Outputs. Output: a NumPy array or pandas data frame containing the transformed features. The shape of the output data will be the same as the input data, but the values will have been transformed according to the specific implementation of the transformer. Steps. Step 1. The input data is passed to the transformer. Step 2. The transformer applies the specific transformation to the input data. This transformation will typically involve applying a mathematical function to each individual feature. Metrics. Metric 1 depending on the specific transformer. Metrics such as accuracy, precision, recall, F1 score, or mean squared error may be used to evaluate the performance of the transformer. Visualization plots. Visualization plot 1. Scatter plots, histograms, or box plots can be used to visualize the distribution of input features and output features. This can help to understand the effect of the transformation. Fine-tune parameters. Parameter 1. Many transformers have parameters that can be adjusted to fine-tune the transformation process. These parameters may include things like scaling factors, thresholds, or other parameters specific to the transformation. Uncertainty methods. Uncertainty method 1. Confidence intervals or prediction intervals can be used to quantify the uncertainty associated with the transformed features. Challenges and fixes. Challenge 1. Overfitting. If the transformer is not properly tuned or if the training data is too small, the transformer may overfit to the training data and perform poorly on unseen data. Sample use case that resulted in challenge 1. A transformer that scales the input features may overfit if the scaling factors are chosen based on the training data alone. This can lead to poor performance on unseen data that has different scaling. Fixes to challenge 1. Use cross-validation to tune the parameters of the transformer and to evaluate its performance on unseen data. Challenge 2. Data leakage. If the transformation is applied to both the training and test data, it can introduce data leakage. This occurs when information from the test data is inadvertently used during the training process. Sample use case that resulted in challenge 2. If a transformer is used to scale the input features, and the same transformer is applied to both the training and test data, the scaling factors will be influenced by the test data, leading to data leakage. Fixes to challenge 2. Apply the transformation only to the training data and then use the learned transformation parameters to transform the test data. sklearn, Base. Outlier mixin. Description. The outlier mixin is a base class in scikit-learn that defines a common interface for outlier detection methods. It provides a standard way to handle outlier detection, ensuring consistency across different outlier detection algorithms by inheriting from outlier mixin. Outlier detection models can be seamlessly integrated into scikit-learn's pipelines and workflows. Inputs. Data input data in the form of a NumPy array or a pandas data frame. The data should be numerical. Outputs. Outlier labels an array or list indicating whether a data point is an outlier. This could be a binary label 0 for inlier, 1 for outlier, or a score representing the likelihood of being an outlier. Outlier scores an array or list containing outlier scores for each data point, quantifying the degree to which they deviate from the expected behavior. Steps. Data preparation. Pre-process the input data, potentially including feature scaling or transformation. Outlier detection. Apply the specific outlier detection algorithm to identify outliers based on the chosen method, e.g., distance-based, density-based, clustering-based. Metrics. Precision measures the proportion of correctly identified outliers among all detected outliers. Recall measures the proportion of correctly identified outliers among all true outliers. F1 score, a harmonic mean of precision and recall, providing a balanced measure of performance. Area under the ROC curve. AUC measures the overall performance of the outlier detection model, considering the trade-off between true positives and false positives. Visualization plots. Scatter plots visualize the data points, potentially highlighting outliers with different colors or markers. Box plots show the distribution of each feature, highlighting outliers that fall outside the typical range. Density plots visualize the density of data points, allowing for the identification of regions with lower density that might indicate outliers. Fine-tune parameters. Threshold. Adjust the threshold used to classify data points as outliers based on their outlier scores. A higher threshold will result in fewer outliers being detected. Contamination. Specify the expected percentage of outliers in the data, influencing the model's sensitivity to outliers. Uncertainty methods. Confidence intervals estimate the uncertainty associated with outlier scores, providing a range of plausible values for each data point. Bootstrapping. Resample the data multiple times to assess the variability of outlier detection. Results. Challenges and fixes. Challenge 1. Dealing with high dimensionality. Sample use case that resulted in challenge 1 when working with datasets with a large number of features. Outlier detection algorithms may be less effective due to the curse of dimensionality. Fixes to challenge 1. Dimensionality reduction techniques like principal component analysis (PCA) or tsna can be applied to reduce the number of features and improve performance. Challenge 2. Identifying outliers in complex datasets with nonlinear relationships. Sample use case that resulted in challenge 2. Outlier detection methods based on distance or density may struggle to identify outliers in data with complex structures that cannot be easily captured by linear models. Fixes to challenge 2. Employ outlier detection algorithms designed for nonlinear data, such as isolation forest or local outlier factor LOF. Challenge 3. Handling skewed data distributions. Sample use case that resulted in challenge 3. If the data is skewed, common outlier detection methods may be biased towards identifying outliers in the tail of the distribution. Fixes to challenge 3. Transform the data to have a more symmetric distribution, or use outlier detection algorithms that are robust to skewed distributions. Challenge 4. Setting an appropriate threshold for outlier detection. Sample use case that resulted in challenge 4. Choosing a threshold that is too low may lead to false positives, while a threshold that is too high may miss true outliers. Fixes to challenge 4. Use domain knowledge or expert insights to inform the selection of a suitable threshold, or employ techniques like cross-validation to optimize the threshold based on performance metrics. Challenge 5. Handling missing values. Sample use case that resulted in challenge 5. Missing values can introduce bias and affect the accuracy of outlier detection algorithms. Fixes to challenge 5. Impute missing values using appropriate methods, or use outlier detection algorithms that can handle missing values. sklearn, base, class name prefix features out mixin. Description: this mixin class is used by scikit-learn transformers to ensure that the feature names of the transformed data are prefixed with the class name of the transformer. This helps to avoid name clashes when using multiple transformers in a pipeline. Inputs. X. The input data, typically a NumPy array or pandas data frame. Y. The target variable, if applicable, typically a NumPy array or pandas series. Outputs. X out the transformed data. Steps. The transform method of the transformer class is called to transform the input data. The output feature names are generated by adding the class name of the transformer as a prefix to the original feature names. Metrics. No specific metrics are associated with this mixin class. Visualization plots. No specific visualization plots are associated with this mixin class. Fine-tune parameters. No specific parameters are associated with this mixin class. Uncertainty methods. No specific uncertainty methods are associated with this mixin class. Challenges and fixes. Challenge 1 none. Challenge 2 none. sklearn. Features election. Selector mixin. Description. The selector mixin is a base class in scikit-learn's features election module that provides a common interface for feature selection methods. It defines the essential methods for transforming data by selecting relevant features. Inputs. X. The input feature matrix, typically a NumPy array or pandas data frame, representing the data for which feature selection will be performed. Each row corresponds to a sample, and each column represents a feature. Y. The target variable, typically a NumPy array or pandas series, representing the labels or values that the feature selection process aims to predict. Outputs. Transformed X. The output feature matrix, which is a subset of the input features based on the selection criteria. The shape of this output will depend on the specific feature selection method used. Steps. Feature selection algorithm. The selector mixin class does not implement any specific feature selection algorithm. It is a base class that provides the framework for various feature selection methods. The actual feature selection logic is implemented in derived classes like select k-best, select percentile, or select from model feature subset based on the selected algorithm. The derived class determines the subset of relevant features from the input data. This subset is then returned as the transformed X output. Metrics. None. The selector mixin class itself does not have specific metrics. The evaluation of the feature selection performance depends on the specific algorithm used in the task at hand. Common metrics used in feature selection include accuracy, precision, recall, F1 score, and AUC for classification tasks, and R-squared, RMSE, and may for regression tasks. Visualization plots. None. The selector mixin class does not provide visualization methods. Visualization techniques, such as heat maps, scatter plots, and feature importance plots, can be used to visualize feature selection results depending on the specific algorithm. Fine-tune parameters. None. The selector mixin class does not have fine-tune parameters. Parameters for tuning are specific to the derived feature selection algorithm. For example, select k-best has a k parameter to control the number of features to select. And select percentile has a percentile parameter to specify the percentage of features to select. Uncertainty methods. None. The selector mixin class does not have uncertainty methods. Uncertainty estimation depends on the specific feature selection algorithm used. Some algorithms, like feature importance-based methods, might provide measures of uncertainty associated with feature selection. Challenges and fixes. Challenge 1. Overfitting. If the feature selection process is not carefully designed, it might overfit to the training data, leading to poor performance on unseen data. Sample use case that resulted in challenge 1: selecting features based on a small data set with high variance might lead to overfitting, as the selected features might not generalize well to new data. Fixes to challenge 1. Cross-validation. Use cross-validation to evaluate the performance of the feature selection algorithm on different subsets of the data, which can help detect overfitting and improve generalization. Regularization. Use regularization techniques, such as L1 or L2 regularization, during the feature selection process to penalize complex models and prevent overfitting. Feature importance. Select features based on robust feature importance measures that are less prone to overfitting. Challenge 2: feature redundancy. The selected features might be highly correlated or redundant, leading to less informative and less efficient models. Sample use case that resulted in challenge 2: selecting features based on correlation alone might result in selecting multiple features that are highly correlated, leading to redundancy and reduced model efficiency. Fixes to challenge 2. Feature selection algorithms. Use feature selection algorithms specifically designed to address redundancy, such as recursive feature elimination (RFE) or select from model with a sparse model. Feature transformation. Apply feature transformation techniques, like principal component analysis (PCA) or linear discriminant analysis (LDA), to reduce dimensionality and eliminate redundancy. Feature engineering. Carefully engineer features to eliminate redundancy and create more informative features. sklearn, base, clone. Description. The clone function in sklearn, base creates a deep copy of an estimator. This means it creates a new instance of the estimator with all its parameters and attributes initialized to the same values as the original estimator. This is useful for various scenarios like hyperparameter tuning. Cloning allows you to create multiple copies of the same estimator with different parameter settings for exploring the search space effectively. Ensemble methods. Techniques like bagging and random forest involve creating multiple copies of the same base estimator, each trained on a different subset of the data. Pipelines. When building complex pipelines, you might need to clone estimators to avoid unintended modifications to the original estimator. Inputs. Estimator. An instance of an estimator object, e.g., a classifier or regressor that you want to clone. Outputs. Cloned estimator. A new instance of the estimator, completely independent of the original estimator. Any changes made to the cloned estimator will not affect the original one. Steps. The clone function utilizes the copy, deep copy function from the Python standard library to recursively copy all the objects within the estimator, including its parameters, attributes, and nested objects. This ensures that the cloned estimator is a complete and independent copy of the original one, with no shared references. Metrics. Accuracy. This metric is used to evaluate the performance of the cloned estimator on a classification task, measuring the proportion of correctly predicted instances. Precision. This metric measures the proportion of correctly predicted positive instances out of all instances predicted as positive. Relevant for imbalanced datasets. Recall. This metric measures the proportion of correctly predicted positive instances out of all actual positive instances, highlighting the model's ability to identify true positives. F1 score. This metric combines precision and recall into a single value, providing a balanced measure of performance. Visualization plots. Confusion matrix. A visualization that shows the counts of true positives, true negatives, false positives, and false negatives for a classification model. ROC curve. A plot that shows the trade-off between the true positive rate sensitivity and false positive rate 1 specificity at different thresholds for a binary classifier. Precision recall curve. A plot that shows the trade-off between precision and recall at different thresholds. Helpful for imbalanced datasets. Fine-tune parameters. None. The cloning process itself doesn't involve tunable parameters. Fine-tuning is done on the cloned estimator based on its specific hyperparameters. Uncertainty methods. Confidence intervals. These provide a range of values around the predicted output, indicating the uncertainty associated with the prediction. Bayesian methods. These approaches incorporate prior knowledge and update it with observed data to estimate the uncertainty in predictions. Challenges and fixes. Challenge 1. Deep copying complex objects with circular references can lead to infinite recursion and errors. Sample use case that resulted in challenge 1. A custom estimator with nested objects containing circular references, creating a loop in the copy process. Fixes to challenge 1. Check for circular references before cloning. Inspect the estimator structure for circular references. Use a custom deep copy implementation. Implement a custom deep copy function that handles circular references appropriately. Challenge 2. Cloning estimators with mutable objects, e.g., lists. Dictionaries can result in shared references and unintended modifications. Sample use case that resulted in challenge 2. An estimator with a list of features that are modified during training. Cloning might copy the list by reference, leading to changes in the original estimator. Fixes to challenge 2. Use immutable objects wherever possible. Use immutable objects like tuples to avoid unexpected modifications. Deep copy mutable objects. Explicitly perform a deep copy of any mutable objects within a estimator before cloning. sklearn, base, isClassifier. Description. The isClassifier method in scikit-learn's base estimator class is a simple yet crucial function that helps determine whether an estimator is designed for classification tasks. Inputs. Self. This refers to the estimator instance itself. Outputs. Bool. A Boolean value true or false indicating whether the estimator is a classifier. Steps. The method checks if the estimator has a class's attribute. If the class's attribute exists, the method returns true, signifying that the estimator is a classifier. If the class's attribute does not exist, the method returns false, indicating that the estimator is not a classifier. Metrics, not directly applicable. Visualization plots, not directly applicable. Fine-tune parameters, not applicable. Uncertainty methods, not applicable. Challenges and fixes. Challenge 1, misinterpretation of estimator purpose. Sample use case that resulted in challenge 1 using an estimator designed for regression, e.g. linear regression for a classification problem and expecting is classifier to return true. Fixes to challenge 1: ensure that the estimator you are using is designed for classification. Check the documentation of the estimator class to verify its intended purpose. Challenge 2: custom estimators without classes attribute. Sample use case that resulted in challenge 2: creating a custom estimator that performs classification but does not include the classes attribute. Fixes to challenge 2: ensure that your custom estimator implements the classes attribute if it is intended to be used for classification. This allows isClassifier to identify it as a classifier. sklearn, base, isRegressor. Description: the isRegressor method in scikit-learn's base class is used to determine if a given estimator is a regression model. Regression models are machine learning algorithms designed to predict continuous target variables. This method plays a crucial role in ensuring that the correct evaluation metrics and other functionalities are applied to a model based on its intended use. Inputs: estimator, the estimator object whose type needs to be identified. This could be any model from scikit-learn's library, such as linear regression, decision tree regressor, or random forest regressor. Outputs: Boolean returns true if the provided estimator is a regression model. False otherwise. Steps: checks the estimator type attribute of the given estimator. If the estimator type attribute is set to regressor, the method returns true. If the estimator type attribute is not set to regressor, or if it's not present, the method returns false. Metrics: not directly related to the isRegressor method itself. However, regression models typically use metrics such as mean squared error (MSE), root mean squared error (RMSE), mean absolute error (MA), and R-squared. Visualization plots: residual plots visualizing the difference between predicted and actual values can reveal patterns and help assess model performance. Scatter plots plotting predicted values against actual values can help visualize the model's fit and identify potential outliers. Feature importance plots for tree-based models. These plots show the relative importance of each input feature in making predictions. Fine-tune parameters. This method doesn't directly involve parameter tuning. Parameter tuning is specific to individual regression algorithms and their implementations. Uncertainty methods. Confidence intervals: regression models can provide confidence intervals for predictions, indicating the range of possible values. Prediction intervals: similar to confidence intervals. Prediction intervals consider both model uncertainty and data noise. Challenges and fixes. Challenge 1: misusing the method. Attempting to use isRegressor to determine the suitability of a model for a particular task could lead to erroneous conclusions. For instance, a model classified as a regressor might not be appropriate for a specific regression problem due to its limitations or hyperparameter settings. Sample use case that resulted in challenge 1: assuming that a model identified as a regressor is always suitable for a regression problem without considering its specific characteristics or performance on the data. Fixes to challenge 1: it's crucial to evaluate the model's performance on the specific regression task and consider its suitability based on factors like data distribution, complexity of the problem, and the model's ability to handle outliers or noise. Challenge 2. Inconsistency in estimator type attribute. Some custom-defined estimators might not have the estimator type attribute set correctly, leading to incorrect results from isRegressor. Sample use case that resulted in challenge 2. A user-defined estimator class that doesn't define estimator type or defines it incorrectly, causing isRegressor to return an incorrect result. Fixes to challenge 2. Ensure that custom estimators are correctly defined with the estimator type attribute set appropriately to regressor for regression models. If the attribute is missing, it needs to be defined within the class definition.